Welcome to lecture 3 on module 4 of computer organization, in which we will be discussing about the static memories and along with that the different types of the static memories and the cell structure along with the Cmos structure of the static memory cells. However, we have seen the different types of memories. The static memories are the memories that consist of the circuits capable of retaining their state as long as the power is applied, are known as the static memory cells. The RAM cells are usually the static memories that has a capacity to hold the data or the content as long as the power exists. Once the power goes off, all this data that are present in the cells gets erased. So in case of static memories, it has its own advantages as compared to the dynamic memories. The static memories are very fast compared to the dynamic memories. This diagram here shows the static RAM cell, individual static RAM cell which has the capacity to store 1 bit of information. The entire setup or the entire circuit can store 1 bit of information. So as we have discussed, the memory, if SRAM has to store 8 by 8 bit of data, then you should have 8 such circuits. So this circuit will have two inverters that are connected in a crisscross fashion, and it has the transistors T1 and T2 that switches or that is responsible to load the data that is present in the bit line into the cells. So the read and write operations will be enabled by the word line. When the word line becomes 1, when word line becomes 1, these transistors turns on, T1 and T2. T1 and T2 turns on. When the T1 and T2 turns on, there is a short between this terminal and this terminal, which indicates that whatever the status that is present in the bit line, if there is a 1, that gets stored here. If it is 0, it stores 0 in the cell. Similarly here, the complemented value of 1, if B is 1, the B dash will be 0. That will be stored in this cell. So here, now let us assume the state x equal to 1. Let us assume that status x is 1. Now how to read this? If x is 1, y is 0. If x is 1, here you will have 1 and the output value here will be 0. Let us consider x equal to 1. Then the input to this inverter 1 will be inverted and the output will be 0. So the y becomes 0. Now if let us assume that we have already stored logic 1. The state is 1. The cell state, the state of cell is 1. That means it has stored 1 in it. Now a processor wants to read it. When the processor wants to read it, it will enable by pulling up the word line high. The word line will be made high by the processor. When word line is made high, the transistors T1 and T2 gets turned on. When transistors T1 and T2 are turned on, the source and the drain terminals of transistor gets shorted. That internally shorts the bit line with the internal state. So what it does is, when x is 1, during the read operation, when word line is enabled, by making word line is enabled, the condition that is present in the x, the state of x, is loaded into B. That means this bus line is pulled high. 1 means whenever we write logic 1, it is logic high. 1 is logic high. What happens is the bit line will be pulled to logic 1, pulled high. So the state of bus line will be 1 and bus bar, B bar, will be 0. So this bit lines are the data lines that runs throughout from the memory to the processor through some of the registers. So this particular condition gets reflected in the data register. We have MDR register. The corresponding bits are pulled high. It again depends on the cell. Such kind of 8 cells are present. If the MDR size is 8 bits, then you will have 8 such cells to store. Since the individual cells can has the capacity to store only one bit, the 8 bits are transferred to MDR, which in turn will be loaded to corresponding registers. If you want to load the data into the cell, now let us assume we need to load one to this cell. In that case, initially the data that has to be written is to be loaded to MDR register. Let me assume we need to load some 101 some value. Let us assume this particular corresponds to this cell. This data corresponds to this particular cell bit. So you will have 8 bits, out of which let us consider this as B7 bit and B7 bar. Now this cell has to be written with logic 1. What happens is this bit will be directly connected to the bus line B, and complement of that is connected to B dash. What happens is, by default the bit line will be pulled high. This bit line B7 will be pulled high and bit 7 bar will be pulled down to 0. At this state, this word line has to be enabled. The word line has to be made 1. The next process is make the word line high. When word line is made high, the transistors T1 and T2 gets turned on, which in turn shorts these two terminals. These two terminals gets shorted, because of which whatever the charge is present in bit line will be loaded into X. So this particular pin will be pulled high based on the data that is present in B7. If it is 1, it will be pulled high. If it is 0, it will be pulled low. So by this way, the data will be loaded into the cell. This is how it can be elaborated, the read operation. Here the word line is activated to close the switches T1 and T2. The word line will be made 1 so that T1 and T2 transistors are turned on. If the cell is in state 1, the signal on the bit line B is high and signal on the bit bar is low. That is B becomes 1, and when X equal to 1, B becomes 1 and B dash becomes 0. This already we know that B and B dash are always complements of each other. The sense and the write circuit at the end of 2-bit lines monitors their state and sets the corresponding output accordingly. The sense and the write circuits are the intermediate device between the cell and the bus. In between the bus and the cell, this sense and write circuit behaves as an intermediate. Here these sense and write circuits get the control signals such as read write bar and chip select signals. Just the reverse of the previous operation takes place during the write operation. The sense and write circuits drives the lines B and B bar. Instead of sensing their state, it will drive these signals, because we are supposed to write to the memory. So initially B is set to 1 and B bar is set to 0 if you want to write 1 to the cell. If you want to write 1 to cell, then B will be driven to 1 and B dash will be driven to 0. It places the appropriate values on bit lines B and B dash. The appropriate values are placed on B1 and B dash, and forces the cell into corresponding state which the cells retain when the word line is deactivated. So what happens after doing this process? The word line is activated and the data that are present in the bit lines B and B dash are loaded into the internal cell, and once the data is loaded, the word line is deactivated so that the data remains, or the data gets latched inside the cell. So This is how the read and write operations in a static RAM cell takes place. The same cell, what we have already discussed, that is the SRAM cell, can be implemented using the CMOS logic. In case of CMOS logic, the transistors, or sorry, the inverters that are present, in the cell has to be implemented using the transistors, or what we call it as MOSFETs. Metal oxide semiconductor field effect transistors are to be used, and these transistor pairs T3 and T5, T4 and T6 form the inverter latch. The read and write operations will be performed same as the previous, as we have explained previously. The read and write operation will be performed in the same way. The voltage at point X is maintained high by the transistors T3 and T6, while T4 and T5 are off. If T1 and T2 are turned off, the bit B and B dash will have the high and low signals respectively. This is when you write the state 1. The explanation remains same as the previous, only the structure will be implemented using the CMOS logic in case of CMOS cell. We will look into the diagram in detail in the next line. Here in this diagram we have total 6 transistors, out of which T1 and T2 performs the same operation as the previous to activate and deactivate, in the process of activating and deactivating of the word line, whereas T3 and T5 behaves as one inverter pair, and T4 and T6 behaves as a other inverter pair. Now when x is 1, if you want to read this one, you need to turn T1 and T2 on by driving the word line 1, and whatever the data present here will be shorted to B bar and B, and this will be sensed by the sense and write circuit, and corresponding output is given to the data lines. Similarly, the write operation takes place where T1 and T2 are turned on, and the data here will be loaded with 1. So if you want to write 1 to the cell, then this bit B will be 1 and this will be 0. So when you turn on T1 and T2, the 0 flows from this terminal to this terminal, as well as this terminal. So what happens is T3 will turn on, and T6 will turn on. T3 and T6 transistor pair will turn on, and the output at this terminal becomes 1 and output at this terminal becomes 0. If you want to read the data, the same process continues, only the difference is with respect to the sense and write circuit. The sense, if in one case during the read operation, the sense and write circuit senses the data that is present in the bit line, whereas in case of write operation, the sense and write circuit writes or loads the data into the bit line. That is the only difference. This is how a CMOS cell of SRAM works. The static RAMs are said to be volatile because when the power goes off, the contents are lost. Whatever the data that are stored in the cells are lost when the power goes off. The advantage of CMOS RAM cell is it is very low power consumption because the current flows in the cell only when the cell is being accessed. Otherwise, in the previous normal SRAM structure, the T1 and T2 and one transistor in each transistors are turned in the each inverter are turned off, ensuring that there is no continuous electrical path between V supply and ground. So there is a continuous wastage of power in terms of T1 in order to keep the transistors T1 and T2 and one transistor uh, to turn off. So the static RAM can be accessed very quickly. As I said earlier, the static RAMs are very fast. The access time on the order of few nanoseconds are found in commercially available chips. The access time is the time taken to access the data from the memory or to finish the complete operation of fetching the data from the memory is the access time. So the access time will be in the order of nanoseconds for a static RAM, and it is uh, fixed for irrespective of the memory that you are going to access. The SRAMs are used in the applications where the speed is a critical concern. So in most of the devices where you need the speed, in such cases, such applications, SRAMs are more used. In this slide, we will discuss about the dynamic RAM, asynchronous dynamic RAM. Asynchronous means it doesn't dependent on the clock signals. There are two types of DRAMs, synchronous and asynchronous. Asynchronous is the one which doesn't have any control signal in terms of clock signals. It is not dependent on the clock signals or clock pulses. So in case of DRAM, dynamic RAM, the information is stored in dynamic memory cell in the form of a charge on a capacitor. So here the charge is stored, the data is stored in the form of a charge in a capacitor. We know that the capacitor cannot hold the charge for more than tens of milliseconds. The same holds good in case of DRAM as well. Because of which we need a refresh circuit that periodically refreshes and restores the capacitor charge to its full value. So what happens is the charge that is stored in the capacitor gets degraded, and that has to be refreshed or recharged before the content is lost. If the charge drops below a particular threshold, the charge cannot be refreshed back. In order to avoid that, there should be a continuous or periodic refresh of or restoring the capacitor charge to its fuller value. This occurs when the contents of cell are read or when the new information is written to it. So this periodic refreshment occurs when the contents of the cell are read or when new information is written into it. We will discuss about a dynamic RAM cell in the next slide with a proper diagram. The asynchronous DRAM structure is much more simpler as compared to the SRAM. In case of SRAM cell structure, we may need 6 transistors along with a word line and a bit line, whereas here we need only one transistor and a capacitor. So this capacitor holds the data that has to be periodically refreshed. So the word line will enable the if you want to write one to, or if you want to store one in the capacitor, then the word line will be enabled. When word line becomes 1, this transistor turns on, creating a short channel between the bit line and the capacitor. Whatever the charge that is present in the bit line will charge the capacitor. Once the capacitor is charged to its full extent, the transistor is turned off by driving the word line to 0. Means we need to disconnect this connection and the capacitor will have the charge, and this charge, since the capacitor cannot hold the charge for larger time, a few tens of milliseconds, the charge can be present in the dynamic memory cells. So it has to be periodically refreshed. For that we have a refresh circuit that will periodically refresh the charge that is stored in the capacitor. So same way, in order to read the data that is present in the capacitor, turn on the transistor by enabling word line to 1. This will make the bit line to read the data that is present in the capacitor. The charge that is present in the capacitor pulls the bit line to high with the proper circuitry. The bit line will be connected to sense and write signal, where it senses the data that is present in the bit line, and it transfers it further through the bus line to the processor. During the read operation, the transistor in the selected cell is turned on, as I mentioned in our previous slide. There, a sense amplifier, the data, the bit line is connected to the sense amplifier. The sense amplifier connected to the bit line detects whether the charge is stored in the capacitor is above or below the threshold value. If the charge is above the threshold, the sense amplifier drives the bit line to the full voltage representing the logic 1. As a result, the capacitor is recharged to the full charge corresponding to the logic value 1. Similarly, if the sense amplifier detects that the charge in the capacitor is below the threshold value, it pulls the bit line to a ground level to discharge the capacitor fully. Thus, the reading the contents of the cell automatically refresh its contents. So if the capacitor voltage is less than the threshold value, then it means that the data that is stored in the capacitor is 0. And if the charge, if the sense amplifier detects the charge that is above the threshold value, it identifies that the data that is stored in a particular cell is 1. However, the word line is common to all the cells in the row. If you have one row, there will be one cell with the capacitor, and this kind of setup gets repeated. For example, if you want a 8-bit DRAM cell, then 8 such cells will be present. So since this word line that connects individual cells are common, once you read any data corresponding to that, when the word line is made 1, automatically all the cells that are connected to that particular word line gets refreshed at the read and refreshed at the same time. The data that is present in the capacitor will be read as well as refreshed at the same time. In this slide, we will look into a 16 megabit DRAM chip. 16, that is, it can be written as 2 mega into 8 bit. 2 mega into 8 bit. So here the cells are organized in the form of 4K into 4K array. 4K into 4K array. So the 4096 cells in each row are divided into 512 into 8. So it becomes 4096 by 512 into 8 bit into 8 bit. So this is how the arrangement is. So here, in order to address 4096, that is we need 12 address lines, 12 address bits, and 512 we need 9 address bits. 9 address bits. So thus the 21 address bits is used to access a byte in this memory. Total 12 plus 9, that is 21 address lines are required to access a byte in this memory. We will look into detail with the diagram of a 16 megabyte DRAM in the next slide. So this diagram refers to an internal organization of 2 mega into 8 bit dynamic RAM cell. 2 mega into 8 dynamic RAM cell. So here the row address will be of 12 bits and the column address will be of 9 bits. So this becomes 512 into 8. We will have 4096 rows and 512 columns. So here, since in order to see if as such, if we have a separate bus lines for the row address and the column address, we may need 21 address lines. We may need 21 address lines other than RAS and column address row. So in order to reduce this, the pins are multiplexed. We will have the 12 address lines out of in the same 12 address lines or address bus, the row address as well as the column address are transferred. So in order to separate the row address and the column address are multiplexed in the same bus line. So it is necessary for us to separate the row address and the column address. In order to separate the row address and the column address, we have a control signals called row address probe and column address probe. When row address probe is 1 or when row address probe is 0, it will extract the row address from the multiplexed address line. And when column address probe is 0 or when it becomes high, then the column address is latched from the multiplex data. This is how we separate the row address probe and column address probe. Since it is a multiplexed pins, we need only 14 input pins out of instead of 21. So here we can save 6 pins with this particular configuration. So the row address probe will latch the row address and it will be forwarded to the row decoder. So here the row decoder decodes the 12 input into 2 power 12 word line. So the 12 input that the row decoder gets will be converted into 4096 word lines. For example, if 12 bit is all 0, if this input is given to the row decoder, then the output of the row decoder will enable the W0 word line. When the inputs are all zeros to the row decoder, the word line 0 will be selected. Here the first word line will be 0, word line 0, word line 1, and it goes up to word line 4095. Total 4096 word lines will be available. When a particular value is loaded into the row decoder, one at a time only one word line will be enabled, and through which you can one can access or read or write the data of all 512 by 8 cell array. So for example, if you want to write to the memory with address 512 to next 512 data plus 512 values, then you need to choose the word line as W1. So the value that you need to give to the word decoder is 000000000001. Then what happens is, when you choose word line 0 W0 using this address, then it will select first 512 bits, 512 bytes. When you choose W1 as 00 last bit 1, then it will choose W1, which will choose the cells from the address 512 to 1024, yeah, and so on. It continues. It is a set of 512 bytes. Next, which column you need to write. For example, you need to write to the column 2 of word line 0. Column 2 of word line 0. Let us assume you need to write to column 2 of word line 0. At that case, in order to choose word line 0, the row address should be all zeros, and the column address should be 2 in the sense it is 10. There are column address can be column address 0, column address 1 up to column address 512. So you since it is a column 2, it is I think 00, 01 and 10. So it is 9 bit. So this will be the address, first 4, next 4 zeros, and last 1 bit. If you give this address to the column address latch, then it will select the column 2 of word line 0, and you can access the data from that particular You can access the byte from that particular column. So here the sense and write circuits will have the chip select and read and write control signals. Read and write will indicate, these are the control signals that are generated by the processor, that will indicate whether the dynamic RAM has to receive the data or transfer the data. This is how a 2 mega into 8 bit DRAM cell works. As we discussed earlier in the previous slide, we have the higher order address which is of 12 bits that constitute the row address, and lower order address 9 that address the constitute the column address. To reduce the number of pins needed for the external connections, we have a multiplexed 12 pins. So 12 pins, out of which the 12 will be address, and the same 12 pin will behave as a 9 column address. So during the read or write operation, the row address is applied first, and that will be latched using the row address strobe signal. The row address latch in response to the signal pulse on row address strobe as the input. When the row address strobe is applied, it will latch the row address. The read operation is initiated in which all the cells on the selected row are read and refreshed. Only the selected rows will be read and refreshed. The row will be selected by the based on the input from the input that is given from the row to the row decoder. Shortly after the row address is loaded, the column address is applied to the address pins and loaded into the column address latch of the column address strobe. After the row address is latched, the column address will be latched using the column address strobe signal. The information in this latch is decoded and an appropriate group of 8 sense or write circuit is selected. If the read write control signal indicates read operation, the output values of the selected circuit are transferred to data lines, same as the previous. During the read operation, the control signal will sense the data that are present in the cell, and it loads it into the data lines, whereas during the write operation, the data that is present in the data lines are transferred into the cells. The information is then used to override the contents of the selected cells in corresponding 8 columns. As per the discussions in our previous slide, we have discussed how individual byte of data can be accessed in a 2 mega into 8 bit DRAM cell. So if the suppose if we want to access the consecutive bytes in a selected row, I said that we in one row we will have 512 bytes, 512 bytes, or 512 into 8 bits in the column. So what happens is, if you want to access the continuous data, for example, you will have the data that are in the column 0 to 511 column address will be there, and in each column you will have 8 bits of data. In each column you will have 8 bits of data. Total you will have 512 such bytes, 512 bytes will be present in the 2 mega into 8 DRAM cell. Now in this case, even without changing the row address, we can access 512 bytes of data. 512 bytes of data. You just need to change the column address. You need to just switch on from the one to other column address continuously up to 512. Thereby, the continuously we can access 512 bytes of data, not even without mentioning the row address. This way of accessing the data is called as the fast page mode. Here all the latches are loaded when the row is selected, and different column address are applied to select the different bytes on the data lines. Thereby you can access multiple datas without changing the row address, which will enhance the speed of transfer of data between the memory and the processor. So here the consecutive sequence of column address can be applied under the control signal CAS. CAS will latch the column address, and the continuous address will be sent to the column decoder or column address without even reselecting the row. The row is fixed. Since in a single row we will have 512 bytes of column, 512 columns, the column address will be kept on changing so that the data can be accessed at a much faster rate than the random access. So the small group of bytes is referred to as block, and the larger groups as the pages. This transfer capability is referred to as the fast page mode. In this slide, we will identify the difference between the static RAM and the dynamic RAM. So the static RAM consists of the circuit that are capable of retaining the state for much longer time as long as the power is applied. In case of static RAM, the data will be present in the memory, or data can be stored in the cell till the power supply is present. Once the power goes off, the data gets erased. The volatile memories becomes because their contents are lost when the power is interrupted. This SRAM is called as the volatile memory, since their data gets lost when the power is interrupted. So the access time in case of RAM is fixed, that is in terms of few nanoseconds. We have seen that the static RAM and the dynamic RAM, the major difference is with respect to the number of transistors. In case of dynamic RAM, you need only one transistor plus one capacitor, whereas in case of static RAM, you need 6 transistors in CMOS implementation. So obviously the static RAM will be much costlier as compared to the dynamic RAM. But the major drawback in case of dynamic RAM is it does not retain their state indefinitely. The capacitor, as we know, the feature of the capacitor, that the charge that is stored in the capacitor gets degraded after a certain time. So you need to continuously refresh or periodically refresh the data or the charge that is stored in the capacitor so that the data is retained for longer time. So these contents may be refreshed while accessing them for reading. What happens is the refresh circuit will add some complexity to the device. So the static RAMs are much better than the dynamic RAM in terms of performance, whereas the dynamic RAMs are much better than the static RAM with respect to the cost. When you design a system with the low cost, and if the speed is not a concern, then you can go for dynamic RAM, whereas if you are very specific with the speed and access time, then the static RAM is the best choice as compared to the dynamic RAM.